guys, we're doing that from Music Box and we're completing the objectives for the Menu Maker Challenge. I'm sure you can all read the names. If you want me to say them out, I will.
Maybe not final.
Yeah, that's not good.
Right, so I'll introduce the problem. So as you may know, Venus is not a nice place. It is rather hellish with its 423 degrees Celsius surface and 400 atmosphere pressure. Understandably, this isn't very good for electronics, computers, etc., etc. And this has actually been tried by the Soviet Union in the 1970s. So for example, the first one to land was Venera 7, which lasted 23 minutes. 23 minutes. Sure, it did hit the surface at 37 miles per hour, but never helped. The next one to land was 8 and 9. The longest any of them survived was about 2 hours, 123 minutes. So, as you can imagine, you're spending a lot of money and you are sending something to Venus that will survive for a couple of hours. It's not the best solution. It'd be good if we could send something there that stays there. But of course, this is hard to do without some sort of advanced way of keeping storage without the need of a computer. So the task that we're given is to make a hard drive that would be able to work in these conditions, which is quite hard considering the conditions are really not nice. So the solution that we came up with, we actually looked to the past because all our modern new technology won't work. It will burn, it will not work, it will be white. So we decided to go back to the old concept of the old music box and punch hole computers, where you would put the card in and it would read it as a binary. So what the idea is that we send down a rover or lander that lands on the surface and starts taking data and then uses an actuator to punch it into a thin sheet of metal. And then you make essentially a punch card with dents instead of holes. We'll get onto that later. And then you can then use that to transmit it back to a spacecraft or a satellite using an orbit around the planet Venus. Yeah.
Okay, this one's me. Oh, this one, alright. Our inspirational source came from what's debated to be one of the first computers to go. I can never say their name, I'm just going to call it an ABC because I will stutter and that's not good. Now, the reason this is debatable is because it's non-programmable and it's not Turing complete, but it was made around World War II in Iowa State College's basement, and it's mostly mechanical based. So it has this mechanical magnetic drum that turns around and it reads up the binary of that and sends the computation, the application rules and memory separate. So we took that, we took away some of the electronics that made this work, the capacitor, the logic gates, and we were left with what we now have, which is purely a reader that transmits the dents into binary, which you'll see in the next slide.
Okay. So in terms of generating these dents, we theorized that we could use an electromagnet to pull a hammer-like thing into the metal, into a mold. Then the reel will keep going around and then just spool up the data into a single chunk. These chunks are basically in binary. So depending on how wide we have the sheet, we can have more bits along it. So we can parallelize the data. And we did do some theorizing of like if it was a millimeter wide and 8 bits long, the megabyte that we have in the spec would be a kilometer of metal. But if we can optimize it more and get a shorter distance between bits or bytes, then we'll be able to have a much shorter, more compact system.
Yeah, so this is just an example of how the satellite would work. So it uses the mirror system, because obviously it's hard to transmit from the surface of Venus because it's Venus. Any sort of traditional transmitting equipment wouldn't fare too well in those conditions. So we come up with a system that is totally mechanical, and actually most of the work is done really with the orbiter, which you would usually send with the lander, like Cassini-Huygens, for example. So the idea is you have a satellite in orbit that beams down radio waves, or UV, we'll get onto that later, and then using reflecting mirrors to reflect the signal back up. And using the dents, you can actually make the mirror actuate up and down, transferring it into binary. So So not much translating actually has to be done by the lander/rover.
Yeah, so that's shown here in this kit. It's basically the dents can be read by, so it's similar to a linear dial test indicator that you use for machining. You can just get a very small change in height and amplify that using like gearing and mechanical advantages to create a slight angle change for the reflector. So then it would either hit the satellite or just reflect up into space. So reflecting up into space becomes a 0, and then hitting would count as a 1. So you can send back that data there.
Yep. So we would also want to store as much information as possible. So what we would like to do is to make it rewritable. Therefore, we would look at memory-shaped alloys. So we would we came out with 2 ideas in order to do this. We've got the first option, which is by having a piece of metal, we would put a resistor and a voltage across it, and apply a small voltage, and it would increase the temperature. Therefore, with that change in temperature, the bunks would go back into how they used to be, so more information could be stored. And the second option is to put it across some rollers. So you need some sort of a ductile material. Therefore, when you pass through the rollers, it would thin the sheet, the metal sheet again. So you need a malleable material, and you would be able to store more information after that.
Okay, so we're on to the pros and cons of this. Now, the cons are quite extensive because, again, it's Venus. It's a hell planet, for lack of any other word. The fact that we're reusing it and rewriting it means the metal will degrade over time. That's just an undeniable factor of it. There's nothing we can do about that, really, as yet. Transmission of data is limited, as the atmosphere of Venus, it stops most visible light, it absorbs a lot of the infrared spectrum too, and radio waves can be obstructed by clouds, which Venus has a lot of. So we're considering mostly UV, or if we have to, we will have to just stick with radio waves. The bright side is, this will last longer than 2 hours, which has never been done before, and that's pretty cool. We'll learn more about Venus, we'll get some facts that even the Russians don't have. So, all in all, I think it's quite a good idea.
Yeah, it's just a list of sources.
Please feel free to check them out.
Any questions then?
Yeah, any questions?
What's the temperature and pressure at the ground?
462 degrees. So
462 Celsius.
yeah.
Celsius and like 90 atmospheres.
And what's going to happen to your, what method are you going to use?
We would use an alloy of nickel, titanium, palladium,
Right.
which can withstand temperatures up to 500 degrees.
And it's going to go through UV and radio. How much so far of Venus has been, if you like, the ground has been successfully tracked?
Not much. There was a linear polarization method that worked briefly in that it scanned strips, but it only showed a horizontal section of it. It couldn't cover much more than the planet. I think it's only a few kilometers.
Do you have any idea how long it took them to do, whether that was consistent in the information?
It did depend. I think there's quite a bit of scattering over the volcanic activity tended to scatter up quite a lot of that data.
You know where you'd land?
NASA do actually have something at the moment called, I can't remember, I think it's the REEA, REA, I think, probably which is current plan for a clockwork rover, which is a rover project so you can move. But I don't think, as far as I know, 'cause obviously that's JPL, but if they have talked about how the hard drive works for that, or if they intend to just do a normal digital one but heavily reinforced, which is hard to do, as the Russians proved. But this could be incorporated in there potentially. So they're already working on systems for Venus surface. This could be into it, or you can almost you could technically have it as a backup if the main one does. Venus gets to it and it doesn't last.
We'd assume NASA has done their research as to where they want to land in that case. We hope.
So, you said 1 megabyte would take up 14 kilometres.
single
kilometer.
1 kilometre.
Mm.
And how long will it take to generate a megabyte of data?
That depends on how quickly you want to turn them over. In theory, there's no limit. Well, there probably is a limit just by the inertia of the hammer.
Yeah.
So however fast you can get that hammer to
So the follow-up question then is, what's your window when you can't get a signal down if you start losing data? Because on your screen, you're going to have some very clever arrangement of tape because you haven't got a kilometre long over.
Well, we're thinking you could use multiple tapes and then have the, what's it called, the arm that comes down?
Signal rate track.
Yeah, well, just have multiple ones and then have a binary digit on each and then run it like that, so that could save space that way. You could even, we looked into different, different reflectivities on different mirrors, so you could do different frequencies at different times to transmit more data at once than just on, off, on, off. So you could have multiple, so say you have both UV and radio, you could have different reflectivity, different mirrors at once and then transmit loads of information at once. With the satellite itself, I'm not quite sure what the orbital period of Venus is, but I'm guessing by its size it's around 90 minutes, similar to Earth.
Is it one of the weird ones that goes backwards or something?
Yeah, it rotates backwards, but the satellite would go around it, orbit it at orbital speed. So you would get a window once every time it orbits. You could theoretically, if you had more, if you had 3, you could constantly receive information from it. But you would need 3 for that because obviously it will go out of range by the time the next one comes back.
You said it was 462 atmospheres. Right? The pressure, ground pressure.
Degrees.
No, pressure.
Pressure.
pressure
What was that? How much? 90?
90 bars.
90 bar, 90 atmospheres.
Yeah.
How are you going to move a hammer against 90 atmospheres? What's your thought about how you would make that mechanism work? Because 90 atmospheres, you're pretty flat as a pancake, so you've got to move against it. You're going to have some way, if it's mechanical, of moving against that pressure. So how are you going to do that? Even if it's a slight amount.
We were going to use an electromagnet.
Mm-hmm.
So it's quite a simple design because you can't have silicon chips on board these. You can have silicon carbide that works at these temperatures, but it's expensive and not as reliable. So an inductor, that will work in all environments.
Electromagnet should be strong enough to...
Yeah.
Again, these dents don't have to be big as well.
No. They wouldn't.
Although the atmosphere is dense, it's a high pressure, but the density of that atmosphere may not, like, compared to the metal, it can smooth through it.
Good.
Sorry,
How would you see like where you're about to land? Like, because I take it like a past thing is land, you can like see where it landed. Like then the surface is changing.
Yeah, so the interesting part of that, a lot of that is done beforehand. So if you scan, they've done lots of, again, UV scans of Venus' surface, so you know about where you want to land, but when you land, because there is a time delay between the Earth and Venus, it takes, depending where it is on the orbit. So again, if it's the opposite side of the sun, you can't communicate. But depending on the distance, there can be a time delay, because the amount of time it takes for the light, the information to get there and back. So all of, and this is the same with Mars rovers as well, the whole landing process has to be totally self-containing and automatic, which is terrifying, especially like the Curiosity rover. It has to do hundreds and hundreds of calculations independently of the ground, of Earth. So it has to work out its own altimeter by using lasers and stuff like that. Venus is actually slightly easier in that respect, in that there's a huge atmosphere, a parachute will stop you. With Mars, it won't. You have to use rockets too.
Theoretically, you could fly a plane in Venus going 8 meters per second if you could survive the burning and all that. So the atmosphere is dense enough that you won't land at a huge speed.
Unless you're the Russians and try to
Yeah,
miles
that's
per hour.
we don't do that.
It worked. Having hit the surface, it still worked.
23 minutes.
23 minutes. That's Venus.
Okay. Any other questions?
All right, thank you very much.